Hello, my name is Michael. I am a third year civil engineering student at UC, and I'm taking CVE 2005 Fluid Mechanics. This will be my first homework for the class, so let's get right into it. So, Fluid Mechanics homework number one, Part A. Uh, our problem statement is derive an expression for the viscosity of a fluid as measured in a cuvette cell with inner radii, outer radii, common wetted height, torque, and angular frequency. So the first thing I'm going to do is I'm going to draw a diagram to better understand the problem. So let's label this. Forgive my handwriting here. So what this is going to look like is we're going to have a motor attached to a smaller cylinder, which is inserted into a larger cylinder, and usually there is a gap for air right here. And our liquid or fluid would be between these two cylinders. I'm also going to create a top-down view off to the right here, just to get a better idea of what our radii are going to be. So next I'm going to list our variables that we're going to be using to derive our expression. So this connected to our smaller cylinder will be rotating, thus creating a torque force on our fluid. So we will list out torque. We have our two radii, Ri and Ro. We will also list. We have our common wetted height here of our cylinders, which will be a little h. And our angular frequency, which we'll write over here. Will be omega, and will be measured in radians per second. And of course, our absolute viscosity that we are trying to derive an expression for, which will be mu, and is measured in Pascal seconds. So this fluid that we're going to be solving for is a Newtonian fluid. And Newtonian viscosity is shown as this equation, which is shear stress equal to the absolute viscosity times the shear rate. So we'll label these shear stress and our shear rate. So I want to take a quick look at the shear rate. So the shear rate is the rate of change of the velocity in the direction perpendicular to the velocity. So I'm going to create a diagram basically showing this relation for our Newtonian fluid. So here we have the velocity in our angular direction. Because remember, this cylinder is moving, so we have our velocity coming here. And we're going to have radius be our x-axis here. So due to something called the no-slip boundary condition, the fluid that is touching our outer radius will not be experiencing any velocity, but the fluid touching our inner radius will be experiencing the angular frequency times Ri, being our velocity. So I'm going to mark this as angular frequency times our inner radius. This will be our inner radius here, and then this will be our outer radius. So our velocity plot will look something like this. And usually this is for two rectangular plates that are pressed together with the fluid in the middle. But since ours is technically a cylinder, it wouldn't be a straight line, but for our purposes, we're going to approximate it as a straight line. So let's start breaking down this viscosity equation here. So for our shear stress, we can show this as force over area equal to our absolute viscosity, and our shear rate now we know is the differential of the angular velocity over the differential of our radius. So let's start deriving our equation from this for our absolute viscosity. So we can look at force. What is our force that we're looking at? It's the torque. So it would be torque times our inner radius over, what is the area we're looking at? It would be the inner cylinder, so 2 pi Ri multiplied by the height equals our absolute viscosity. And then for our angular velocity here, we know that it can be found by multiplying our angular frequency by the radius, but we also know that when angular frequency is multiplied by our outer radius, it will go to 0. So we have angular frequency times Ri minus angular frequency times Ro, but we know this is 0. So this is gone. Over our outer radius minus our inner radius. And now we can solve for our absolute viscosity. So the expression we end up getting is our absolute viscosity is equal our torque multiplied by our outer radius minus our inner radius over 2 pi inner radius height times angular velocity. And this is our expression for the absolute viscosity of a Newtonian fluid.